So it's time, since we've done some exploring of 3 different examples, it's time for us to decide on some type of equation that models exponential growth. And if you will look at the page 52, it should look like this one. And up the top, there we have a definition of an exponential function. It says the variable is in the exponent spot. Well, sure enough, look, there's x right there, and it makes the graph increase or decrease at a rapid rate. So again, let's try to do some notes on this. And if you will look with me right down at the bottom. Let's get on it here. This is growth. So what do we know? Well, x is in the exponent spot for it to be an exponential function. So that's the first thing. That's what you're going to notice. So the exponent is x in an exponential function. This a value, this number out front right here, this is the initial amount, or how much is there when x is 0. Oops. So when x equals 0, this is how much we have, right? What's the y value when x is 0? Well, whatever a is, okay? A is the initial amount. So a is the initial amount, or the value when x equals 0. That's two different ways to say the same thing. So we know x is the exponent, a is some number, and if you don't see a, it's understood to be 1, right? We have the decay down here. This is growth. So our first two examples we did, the curve looks like this. The second example that we did, or the third example that we did on vocabulary words, the graph looked like this. So from an equation, how can you tell if it is exponential? Well, you're going to look in the exponent spot and see where x is. If x is in the exponent spot, it's exponential, period. Okay, period. How can you tell from a graph? Well, it's going to be this J-shaped curve. So let me just kind of extend this. It's flat over here, and then whoosh, it looks like it's going straight up, but it really doesn't. It goes out just a smidge. This is exponential growth. How about this one? Well, again, this one extends and flattens out, and it looks like it's approaching 0. How about on this side? It goes up almost straight up, but it goes out just a little bit. So this is growth, this is decay, and these, we can call them the curves. But what shape are they? It's not a U-shaped curve like we had with quadratics. It's what we call a J curve. I mean, it's exponential. It's J-shaped. You see that, like the letter J right there. You could also call it a slide. So that just visually helps you think about what the curve is. But it is an exponential curve. And if you've been looking at the news at all, that's how the virus is growing. So from an equation, how do we know it's exponential and not linear? Well, where's x? If x is in the exponent spot, it's an exponential function. How can we tell by the curve? Well, we're going to look and see, does it have this J-shaped curve? If it's a J-shaped curve, we know it's exponential. Remember, linear is a straight line, right? Because all lines are straight. A parabola is the U-shaped curve. So how is this different? Well, it's this slide or J curve. So below, you have some tables. And what we want to try to do, so we can tell if it's exponential from the equation. We can tell if it's exponential from the graph. So the next thing is, can we tell if it's exponential from a table? And that's what we're going to practice on here. We've got some examples. It says, determine whether each set of data shows exponential behavior, right? Yes or no, and then explain why or why not. And we said earlier that if it's exponential, it grows at a constant ratio. So let's look at these y values and these x values. -3 to -2. Okay, that's +1. -2 to -1. That's +1. -1 to 0. That's +1. How is y changing? 9 to 12. Well, that's increasing, so I'm either adding or multiplying. If I were adding, it would be +3. But if I were adding, it wouldn't be exponential. It would be linear. 12. 12 to 15. So what does it look like I'm doing each time here? That's right. I'm adding 3, +3, +3, +3. So now the question is this exponential? And our answer would be no, it's not exponential. Why? Well, am I multiplying by the same thing down the y column each time? What am I doing? I'm adding the same thing. So it's not exponential, and the question is why or why not? Well, because I'm adding 3 each time down the y column. I'm adding 3. That's my rate of change. So that means it's linear. Okay? Let's look over at example number 6. What is my x value doing? Well, from 0 to 5, that's 5. From 5 to 10, that's 5. From 10 to 15, that's 5. And what are my y values doing? 20 to 10. Well, that's decreasing, so I'm either subtracting or dividing. Let's see, 20 to 10 minus 10. So am I subtracting 10 each time? No, I'm not, am I? Because 10 minus 10 is not 5. 5 minus 10 is not 2.5. So I'm getting smaller, but I'm not subtracting. So that means I must be multiplying by a number less than 1. Let's see if that's the case. So how did we find the ratio before? We took the second number divided by the first. So I'm going to come over here and say 10 divided by 20 is 1/2, or 0.5. Okay, next one. 5 divided by 10 is 1/2, or 0.5. So now what? 2.5 divided by 5 is 1/2, or 0.5. So what we can do is we can figure out what is this exponential? Well, am I multiplying by the same thing each time? A half, a half, a half. Yes. So we would say, yes, it is exponential. And what am I multiplying? Why? Because you have the number I'm multiplying by each time, my base, okay, I have a constant ratio. I have a half. Over here, I was adding. Well, that was linear. But here, I'm multiplying by the same thing each time. So my base is a half. Let's try to kind of get a thought about this. Um, I could even come back and write the equation. We'll save that for the next example. But what did we see in this example? We saw that we can tell from an equation if it is exponential by x is in the exponent spot. From a curve, we can tell if it has this J-shaped curve, just one of them. If it has one J-shaped curve, that's growth. If it has one J-shaped curve this way, that's decay. From a table, we can tell if we look down the Y column and see, how am I changing? If I'm changing by adding, nope, adding the same thing each time is linear. Am I changing by multiplying by the same thing each time? And if that's the case, then yes, it's exponential.